Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Instrumentation and Measurement. This is lecture number 1. In this lecture, we will explore why should we study instrumentation and measurement. We will also see the basic structure and definitions that are being used in measurement and instrumentation systems. We will see also some block diagrams of some common measurement systems, and then finally we will conclude today's lecture with the syllabus. So why should we study this course? Measurement is an essential activity in every branch of technology and science. We will see with some examples. For example, we need to know the speed of a car. And not only the speed of a car, we also need so many sensors so that this car can work efficiently. So one application is the technology and products in which sensors or measurement system play a vital role by providing the information to either, for example, the driver, or directly the sensors are connected to the automatic controller, which is also called engine control unit, for example. We also need to know the temperature of our working environment. For example, there are plenty of sensors that we need to know about our environment. For example, the VOC. What VOC is? The VOC is the volatile organic compounds, which are carbon-based compounds, and they easily evaporate at ordinary room temperatures. And some of these VOCs are very harmful, and a continuous low-level exposure often causes long-term health effects. So the measurement is also an important tool to know about our environment and society. This is an example of a tiny VOC sensor. And more you can explore on the links that I have provided here. Sometimes it is also necessary to find and to know the flow rate of a liquid in a pipe. For example, here, a flow through the pipe is controlled by a control valve, but the control valve should be controlled by a controller, and the controller should know the flow rate. So an orifice plate and a dB transmitter is used to tell the controller what the flow rate is currently, and then according to the set point, the controller will manipulate this control valve. This is an example of a flow measurement device. And according to the situation, for example, if the flow is liquid flow, this is an example in which the volumetric flow is measured here, 430 cubic feet per meter. It goes through this pressure drop valve, and after that the second volumetric flow meter downstream is able to read it properly because liquids are incompressible. But in the second case, when we have a gas flow, the volumetric flow is reading 430 cubic feet per meter, but after a pressure drop, the gas will expand and the volumetric flow will be like 736 cubic feet per meter per minute. So in this situation, we need to know about the situation, and we need some computer to make the proper correction here, and the correction will be based on this pressure drop. So there will be some formula in which we will have these pressure informations, and then we will be able to exactly calculate this value. So this is another good application of measurement, industrial automation area. We also need to know, for example, the oxygen dissolved in a river. This is an example of a measurement system in a river that is able to calculate the amount of oxygen dissolved. It may consist of so many devices, like for example multi-parameter sonnet, submersible pressure transducer, integrated data logging system, and then telemetry, and then a live data transmission. You can go and watch a very good demo about this multi-parameter zone. This is a good application of water and ecosystem. You see, this is a live monitoring of a river section, in which every 15 minutes this monitoring station takes the measurement for the temperature and dissolved oxygen, pH, and other variables, and the data is transmitted in real time using the telemetry for the remote access. And by this, the EPA is able to know the conditions of the water, the drinking inlet water monitoring at this station. And this is the snap of the real-time data from, for example, July 1 to 23rd September, during this period from June 2019 to October 7, 2019. And this is the dissolved oxygen in percentage. You also need to know the measurement of electricity used in your house. And now the things are becoming smart, so every device that is utilizing the electricity should be properly monitored. So the measurement application in energy and power is like this. So a measurement system is an information system which presents an observer with a numerical value corresponding to the variable being measured. A measurement system may contain five types of sensing elements. Whichever we have seen, it may be like sensing, signal conditioning, signal processing, data presentation, and signal transmission. And they are all applicable and are there in the measurement examples that we have seen. So the simple purpose of measurement system is to link the observer to a process which generates information. So there was a process, whether it was a water system or a car or an industrial process plant, and the measurement system will be connected to this process and make sure that this measurement system will provide a value to the observer accurately. So a process is anything that is generating information. A system that is generating information, it may be a chemical reactor, a car, human heart, or a weather system. Observer, it may be a person or a computer system that needs the information. For example, a plant operator, a driver, a nurse, or engine control unit, for example. Measurement system is that measures the information carrying quantities, processes them, and presents them to the observer. So the simple structure of a measurement system consists of the sensing element, then comes the signal conditioning element, then we have some elements that process the signal, and then we have a data presentation. Nowadays, with the telemetry and control, we can redefine this simple block diagram into this, where the signal transmission is there, and most of the part for signal processing and algorithms and a lot of AI based algorithm developments are done on the offline on the remote computers, and this is going to the control loop. This is an example of a DCS, distributed control system IO unit, and some data goes to the historian. In every plant, just like a black box, they have a historian, so the data is being archived in appropriate protocol, and this data make sure that here the protocol may be different in while you are sending the data here. For example, here mostly might be using the OPC, and here you might be using 4 to 20 milliamps or a HART or a foundation field bus or other communication. So a field instrument may be nowadays a smart sensor consists of combined signal element or signal conditioning element and somehow some signal processing, and then they provided like a proper protocol. Maybe here the data is ready in digital format from the field instrument. If the field instrument is 4 to 20 milliamps, the signal will be 4 to 20 milliamps. If the field instrument is, let's say, hard, then the signal will be transmitted in the hard protocol, and or the other foundation field bus or whatever is, or mod bus, for example. So this is the structure of modern day measurement system, especially focused in industry. So sensing elements are in contact with the process, which is the sensor, and it gives the output that depends on the variable to be measured. For example, a thermocouple, which provides a voltage output depending upon the temperature. That sense strain gauge, it changes the resistance. It provides a change in resistance depending upon the mechanical strain. Orifice plate provides the pressure drop, which depends on the flow rate. Ultrasonic sensor, it provides electrical output, depends on the mechanical forces like vibrations and on the sensor. And some sensing elements depends directly on the physical variable of interest, while others have a more complex connection to the underlying mechanism. Some are linearly connected to, for example, to the temperature, for example, not the thermocouple, but the other metal. This may be nonlinear, and this may be, there are some temperature RTDs, for example, some are very provide a linear relationship. Signal conditioning elements, they are the elements which convert the sensor output to the more suitable forms. And we have deflection bridges, which convert the impedance changes into the voltage changes. We have amplifiers, which actually amplify the millivolts to the volts. And oscillators, they convert the impedance change into a variable frequency voltage. Then in signal processing elements, analog to digital converter is also a kind of a signal processing element, which converts an analog to the digital, takes it to the DSP or the microprocessor or computer. Then computer or DSP chip calculates the values of the major variables given in the digital input, applies an algorithm, do some filtering, and so on. So signal processing elements can also combine values from multiple sensors. This is the sensor fusion in order to calculate some higher level quantity. Now there are some block diagrams. For example, a block diagram of a temperature measurement system. We have, think about a thermocouple sensor. We have true input temperature from here, and the thermocouple is providing millivolts of this. This is an example of IP68 type thermocouple used in industry. After this millivolts, the signal conditioning element, which is consisting of these two components. For thermocouple especially, we need auto reference junction compensation, which corrects the value in case of any problem with the reference junction. So the millivolts are now corrected. So this is like a correction circuit, and then this good value is now correct value is now amplified, and the millivolts will be converted to the volts. This is the signal conditioning part. Here is an example of a chip which from Maxim, which is using thermocouple compensation circuit, and thermocouple is connected here. Then comes the signal processing, which consists of the analog to digital converter and a computer. Here is the example of the EE305, which is showing here as a signal processing part, and this is finally sent to data presentation. It may be an LCD or a computer. For the block diagram of a speed measurement system, here another example, we first have a tacho generator as a sensing element, then a Schmitt trigger for the signal conditioning. Notice that the tacho generator provides a signal in terms of frequency. Schmitt trigger improves and provides a frequency for the counter, and counter counts it, provide a digital output to the computer, and the computer is may use it on to display on the screen. The flow measurement may consist of orifice plate as a sensor, which provides a differential pressure. This differential pressure is transmitted in let's say 4 to 20 milliamps current to ATC, and then ATC and computer together make the signal processing part, and finally the data presentation. It may be a chart recorder or a computer. In old days we used to have these chart recorders. The weight measurement system consists of two sensors. Here we have a primary sensor, cantilever, which provides a strain, and then this strain is changing the resistance of a strain gauge. So this resistance is now used in one of the arms of the deflection bridges, which deflection bridge provides as a change in the millivolts output, and these millivolts are amplified using the amplifier to volts, and then comes the signal processing part again as ADC in computer, and then the final the digital display. So based on all these examples and the applications, what I have done is to put the syllabus into 4 equal parts. The first part will be comprised of the general principles of the measurement system. Then the second part will be consisting of the sensing and signal conditioning. Third will be we will go through some specialized measurement systems which are very job oriented, application oriented, and final part we will review the data acquisition. We will especially study about the data communication and the intelligent instrumentation. The book we will follow is The Principles of Measurement System, 4th edition from John P. Bentley. The reason is because this book provides you from the very basic physical basic sciences principles, uses the mathematics to connect them, and then uses the practical specifications to connect them well. So by using this book, we will be able to understand the basic principles, utilize them into a new situation. We will learn some design principles, and after that you will be able to select the right tools, right instruments, sensors, and you can design the whole measurement system. You can investigate the whole measurement system. So this book is a really good one, and inshallah we will enjoy reading through this book. So I will keep it. So the part 1 will be from chapter number 1, 2, 3. Especially chapter 1 is the introduction. We just went through this one. Chapter 2 and chapter 3. Chapter 2 talks about the static characteristics of the individual elements, and then chapter 3, this is about the overall accuracy calculation about any sort of measurement system. These are the two things. But after completing these two, you will be able to deal with any sensor. It's correct. You can devise the characteristic. You can identify how the sensor is behaving, whether it is linear, non-linear, over the range, and in case of any environmental disturbances, how to take care of it, and make small compensation, either circuits or the software, so that the overall measurement is accurate or correct. And partially we will cover a few items, a few of the things from chapter number 4 to 7. For example, some ideas about the dynamic characteristics, the principle of loading, and effect of the interference and noise, and the reliability. The second part, the second part is about the sensing and signal conditioning, and this is all about some common type of sensing elements, what are their principles, and then signal conditioning, how to design some deflection bridges, and the operation amplifiers, instrumentation amplifiers, and all this stuff. Then we have the third part, which is about the specialized measurement system. It is from chapter 12, 13, and 16. We will focus on the flow measurement system, which is chapter 12, intrinsically safe systems, chapter 13, and ultrasonic systems from chapter number 16. And we will do some real practical calculations for some practical scenarios. Part 4 is interesting, and it will be more industrial or with the current aspects, and what are the current data acquisition systems in place. And because most of the basic ideas you already have learned in your electronic courses, data communication, especially the industrial communication, in use field bus, foundation field bus, HART protocols, wireless communication, and all this stuff we will try to explore as much as possible. And then the intelligent multivariable system, for example, this is the currently the very fascinating field about how to design a soft sensor and improving the some using the AI neural networks to make to fuse the data to gather sensor fusion or the soft sensing, how we can achieve a good measurement system. So this is an intelligent multivariable system about chapter number 19. Thank you very much. For any questions, please don't forget to write me an email. Thank you.